June 7, 1944. Off Omaha Beach, Normandy. Lieutenant Commander Joseph Vaghi stood on what shouldn't exist, a floating steel platform 300 feet long carrying 40 fully loaded trucks across open water. Around him, 23 similar vessels shuttled between Liberty ships anchored 3 miles offshore and the bloodied beaches. Each pontoon section flexed independently as waves passed beneath, yet the structure held. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Rhino Ferry wasn't in any naval engineering manual. It didn't appear in pre-war doctrine. 6 months earlier, it didn't exist even as a concept. Now it was moving more tonnage to shore than all the landing craft combined. The mathematics were impossible by conventional naval architecture. Traditional landing craft, the workhorses of amphibious warfare, carried individual vehicles. An LST, landing ship tank, could beach itself and discharge 30 vehicles directly onto sand, but LSTs were scarce, required specific beach gradients, and became helpless targets while grounded. The DUKW, the amphibious truck praised in every planning document, carried 2.5 tons. 40 trucks on a single trip represented 400 tons of cargo, the equivalent of 160 DUKW runs, 16 LST trips, or incalculable journeys by smaller landing craft. Yet here it functioned, welded together from prefabricated pontoon sections designed for bridge building, powered by outboard motors meant for small boats, and crewed by sailors who had never seen anything like it before training began 8 weeks prior. The invasion of France required moving 171,000 tons of supplies in the first 4 days. Planners had calculated vessel requirements based on existing landing craft capacity. Those calculations produced impossible numbers. More ships than existed in the Allied fleet, more trips than hours available, more beach space than Normandy possessed. The Rhino Ferry solved an equation that conventional naval architecture couldn't balance, but its creation required abandoning every principle that naval engineers had been taught. American amphibious doctrine in 1943 reflected 2 decades of Marine Corps experimentation. The landing craft hierarchy was established: LSTs for heavy vehicles and bulk cargo, LCIs for infantry, LCMs for medium equipment, LCVPs for assault troops. Each vessel type had been refined through Caribbean exercises, tested at Guadalcanal, proven at Tarawa. The system worked within its designed parameters. The problem was that Operation Overlord exceeded every parameter by orders of magnitude. The initial invasion plan for Normandy, drafted in spring 1943, called for 3 divisions landing simultaneously. Logistics officers calculated requirements: 600 LSTs, 800 LCIs, 1,200 LCMs. The combined chiefs of staff reviewed these numbers with growing alarm. The entire Allied landing craft fleet totaled 469 LSTs, 783 LCIs, and 942 LCMs. Even concentrating every vessel in European waters left massive shortfalls. The planned Italian campaign required 300 LSTs. Pacific operations couldn't be suspended. British operations in Southeast Asia had minimum requirements. The numbers didn't work. Commander Edward Ellsberg, a naval salvage expert, had observed similar problems during the North African landings. At Oran in November 1942, insufficient landing craft forced soldiers to wade ashore in water over their heads. Equipment was abandoned in surf. Vehicles were flooded. The beach became a chaos of stranded men and submerged cargo. Ellsberg watched Liberty ships sitting 3 miles offshore, holds full of desperately needed supplies, unable to discharge because landing craft shuttled back and forth carrying partial loads. Each trip took 3 hours, 2 miles out to the transport, offload, 2 miles back to beach, unload, return. In that time, a ship could discharge perhaps 30 tons. Liberty ships carried 10,000 tons. The fundamental inefficiency was architectural. Landing craft were small because they had to beach in shallow water. Small vessels carried limited cargo. Limited cargo required multiple trips. Multiple trips consumed time. Time determined how much could be landed before German counterattacks arrived. The cycle was unbreakable within conventional naval design. Larger landing craft required deeper water, which necessitated longer approaches, which increased vulnerability, which argued for smaller craft. The logic was circular. British engineers approached the problem through specialized vessels. They designed the landing craft Tank Mark 8, a vessel specifically for beaching operations. They created the landing craft Support Large, a fire support craft with armor and guns. Each new design addressed one problem while creating others. The LCT Mark 8 drew more water than smaller craft, limiting its beach access. The LCS Large lacked cargo capacity. Specialization produced excellence in narrow roles, but couldn't solve the fundamental volume problem. American industrial capacity suggested a different approach. Rather than designing perfect vessels that would take years to produce, perhaps functional structures could be assembled from existing components. The idea emerged from multiple sources simultaneously, suggesting less invention than inevitable conclusion. Army engineers had perfected pontoon bridging. The Navy used similar pontoons for floating piers. Both services had standardized cube-shaped pontoon sections, 5 feet by 5 feet by 7 feet, weighing 1,200 pounds empty. These pontoons, designated Monet by the Army and Navy Pontoon Mark II by the fleet, were mass-produced by 23 manufacturers. Production capacity exceeded 30,000 pontoons monthly. The question that nobody had officially asked was whether pontoons designed for static bridge structures could function as dynamic vessels. Naval architecture suggested not. Pontoons were boxes, not hulls. They had no keels, no curves, no hydrodynamic shaping. Connecting them created floating platforms, not ships. Platforms couldn't navigate. They couldn't handle waves. They certainly couldn't cross open ocean carrying 40 trucks. In September 1943, Captain John N. Hughes of the Navy's Bureau of Ships received authorization to explore unconventional cargo transfer methods. His directive, buried in routine correspondence, allowed experimentation with pontoon-based causeways. The term causeway was deliberately vague. It could mean fixed structures or floating platforms. It didn't specify propulsion or cargo capacity. This ambiguity would prove essential when experiments exceeded their initial scope. Hughes assembled a team at the Naval Amphibious Base in Little Creek, Virginia. The personnel reflected the project's improvised nature. Lieutenant Albert M. Doyle was a reserve officer, a civil engineer in civilian life with no naval architecture training. Chief Warrant Officer William D. Sullivan had been a construction foreman. Machinist's mate first class Raymond Kowalski had worked in a Detroit automotive plant. None had designed ships. None were supposed to. They were building floating platforms. The first prototype, assembled in October 1943, consisted of 7 pontoon sections bolted together in a line, 35 feet long, 5 feet wide. Sullivan mounted an outboard motor on the stern. Kowalski fabricated a rudder from scrap steel. Doyle calculated that the structure should float, support approximately 3 tons, and theoretically move through water. Theory met reality on October 19th when they launched the prototype in the Little Creek Basin. It floated. The pontoons, each providing 1,250 pounds of buoyancy, easily supported the platform's weight plus a 1-ton truck. Movement was less successful. The outboard motor's 9 horsepower couldn't overcome the platform's resistance. Water pushed between pontoon sections, creating drag. The structure flexed in ways that would have destroyed a rigid hull, but the pontoon's individual buoyancy prevented sinking. The prototype achieved 2 knots in calm water, unacceptable for operational use, but proof that the concept wasn't immediately impossible. The team spent November revising the design. They added pontoon sections, creating a platform 7 sections long and 4 sections wide, 28 pontoons total. This provided 140 square feet of deck space, sufficient for 4 trucks. More significantly, the wider platform created better hydrodynamic efficiency. Water flowing past multiple pontoon rows generated less proportional drag than single-file arrangements. The revised platform achieved 4 knots with a larger outboard motor. December brought winter storms to the Virginia coast. The prototype remained functional in seas that would have swamped smaller landing craft. The pontoon's independent flexibility allowed the structure to conform to wave patterns rather than resist them. Each section rose and fell separately, creating a snake-like motion that looked alarming but proved seaworthy. Trucks secured to the deck remained stable through the articulation. The discovery was accidental but crucial. Flexibility, considered a weakness in conventional hulls, became strength in pontoon platforms. By January 1944, Hughes had authorization to build a full-scale prototype. The specifications came from cargo requirements rather than naval architecture. Planners needed to move trucks from Liberty ships to beaches. Liberty ships anchored in 20 to 30 feet of water, 3 miles offshore. Standard Army trucks measured 7 feet wide and 20 feet long. 40 trucks required 8,000 square feet of deck space, assuming minimal spacing. Converting square footage to pontoon sections produced the design: 10 pontoon sections wide, 30 sections long, 300 pontoons total. The resulting platform measured 50 feet wide and 210 feet long. Nobody had built a vessel this shape. It violated every principle of ship design. The length-to-width ratio was completely wrong for efficient movement through water. The flat bottom created maximum drag. The lack of hull shaping meant the structure would push water rather than cutting through it. Naval architects would have rejected the design immediately. Hughes wasn't asking naval architects. He was asking engineers to solve a cargo problem. Construction began at Little Creek in February 1944. The pontoons arrived by rail from manufacturers across the eastern states. Each section bore identification numbers stamped during production. The assembly crew, expanded to 40 men, bolted pontoons together following a grid pattern. Army pontoons used special pins that locked sections without requiring tools, allowing rapid assembly under field conditions. The Navy adopted this system, adding welded reinforcements at stress points. The structure grew section by section. After 50 pontoons, it resembled a floating parking lot. At 100 pontoons, it dwarfed everything else in the basin. At 300 pontons, it was longer than a destroyer. The completed platform weighed 360,000 pounds empty, well within the pontoon's combined buoyancy of 750,000 pounds. This left 400,000 pounds of cargo capacity, sufficient for 40 trucks averaging 5 tons each loaded. Propulsion posed the greatest challenge. The platform's size and drag required substantial power. Marine engines weren't available. Ship engines were too heavy. The solution came from an unexpected source. The Navy had recently acquired 320 horsepower Grey Marine diesel engines intended for submarine chasers. The program had been cancelled, leaving engines in storage. Sullivan requisitioned 4 engines, mounting them in separate pontoon sections at the platform's corners. Each engine drove a propeller through a reduction gear. The 4-engine arrangement provided redundancy and maneuverability through differential thrust. The first sea trial occurred on March 3, 1944. The platform, designated Experimental Floating Platform 1, moved away from the pier at 6 knots. This exceeded expectations. More importantly, it handled turning through differential engine speeds. The crew, now 8 men, practiced maneuvering through Little Creek's channels. The platform responded slowly, requiring 30 seconds to begin turning and 400 feet to complete a 90-degree turn. For a structure 210 feet long, this was acceptable. Ocean trials began March 10th in the Atlantic off Virginia Beach. Seas ran 4 feet, considered moderate. The platform wallowed through waves, decks awash with spray, but remained stable. The snake-like flexing observed in the prototype appeared at larger scale. Individual pontoon sections rose and fell 6 inches relative to adjacent sections. The bolted connections held. The platform achieved 5 knots in open water, acceptable for the 3-mile distance from anchorage to beach. Loading trials followed. Army trucks from Fort Story drove onto the platform via a pontoon ramp. The first truck's weight pressed the platform lower in the water. The second truck distributed weight more evenly. By the 10th truck, the platform sat 4 inches deeper, but remained stable. At 20 trucks, deck edges were 18 inches above water. 40 trucks, the design capacity, brought the platform to its maximum draft with 6 inches of freeboard. The margin was narrow, but sufficient for calm seas. The breakthrough came during unloading trials. The platform couldn't beach like an LST. Its flat bottom would ground in 5 feet of water, too deep for trucks to drive off safely. The solution was elegantly simple. 2 additional pontoon sections, each 50 feet long, were connected as a hinged ramp. When lowered from the platform's forward end, the ramp reached the beach. Trucks drove off one at a time. The entire 40-truck cargo could discharge in 20 minutes. This compared to 8 hours for equivalent capacity using conventional landing craft. Captain Hughes submitted his report to the Bureau of Ships on March 20, 1944. The platform worked. It could carry 40 trucks, navigate 3 miles of open water, and discharge cargo faster than any existing vessel. Construction required only standard pontoons, available engines, and basic metalworking equipment. Assembly time was 48 hours with a trained crew. Cost per platform was $42,000, compared to $1 million for an LST. The numbers overwhelmed objections about unconventional design. The Rhino Ferry, as it was now designated, received production authorization on March 25. The name derived from its designation, RHINO, Rapid Hull Invasion Nautical Operation, though some claimed it referenced the platform's unstoppable momentum once moving. Either way, the name captured the ferry's essential character: powerful, ungainly, and effective. Production planning revealed the design's critical advantage. Rhino ferries didn't require shipyards. They could be assembled anywhere with calm water and pontoons. The invasion fleet would carry pontoons as deck cargo. Upon arrival in the invasion area, crews would assemble ferries from these pontoons. This meant ferries could be built specifically for each operation, then disassembled and pontoons reused elsewhere. No vessel had ever been designed for such flexibility. The naval amphibious base at Little Creek became the Rhino Ferry Training Center. 10 ferries were assembled for crew instruction. Each ferry required 8 personnel, a coxswain to command, an engineman for each of the 4 engines, 2 seamen for lines and deck work, and a signalman for communication. Most crew members had never operated any vessel before. Training focused on practical skills, starting engines, engaging transmissions, steering through differential thrust, judging distances, and managing cargo loading. The ferries handled unlike anything in naval experience. They responded slowly to helm changes but maintained course once turned. They couldn't stop quickly, requiring 200 feet to halt from 5 knots. Backing up was nearly impossible due to the flat stern. Experienced boat handlers found ferries more difficult than novices because they had to unlearn conventional techniques. One training instructor noted that the best ferry coxswains were former truck drivers who understood cargo distribution and patience. Assembly training proved equally important. 4-man teams could bolt together a complete 300 pontoon ferry in 8 hours using only wrenches and come-alongs. Welding the reinforcement points required another 4 hours. Engine installation took 6 hours per engine. From loose pontoons to operational ferry required 48 hours, as Hughes had calculated. This assumed calm water, available pontoons, and trained crews. Combat conditions would test whether these assumptions held. By mid-April 1944, 60 Rhino ferries were authorized for Operation Overlord. Pontoon sections were distributed across 148 Liberty ships in the invasion fleet. Each ship carried between 75 and 300 pontoons, bolted to deck cargo or stowed in holds. The ships also carried the grey marine engines, propellers, rudders, control boxes, and welding equipment necessary for ferry construction. Everything except skilled labour travelled in standard cargo. The plan called for assembly to begin immediately after. The beaches were secured. Engineer special brigades, army units trained in shore logistics, would provide assembly crews. Navy Seabees would supervise construction and operate completed ferries. The target was 24 ferries operational by D+2, 48 ferries by D+5, and all 60 ferries by D+7. These ferries would supplement landing craft, not replace them. Combined operations would deliver the tonnage that planning required. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Lieutenant Commander Vaghi, selected to command the Rhino Ferry operations at Omaha Beach, studied the plan with growing concern. The schedule assumed everything would work perfectly. Pontoons would be available. Assembly areas would be secure. Crews would perform under fire. German artillery wouldn't target the ferries. Weather would remain favorable. Any single failure would cascade through the timeline. His experience in the Mediterranean suggested that nothing went perfectly in combat. The fundamental vulnerability was obvious. Rhino ferries couldn't dodge. They couldn't accelerate. They couldn't take evasive action. A ferry loaded with 40 trucks and 200 soldiers represented an irresistible target. German artillery observers would see them coming from 3 miles away. A single shell penetrating a pontoon section wouldn't sink the ferry, but multiple hits could compromise buoyancy. Fire was equally dangerous. Gasoline-loaded trucks burning on wooden decks would destroy a ferry faster than gunfire, yet alternatives didn't exist. The cargo had to move from ships to shore. Landing craft couldn't handle the volume. Direct beaching of LSTs was impossible at Omaha due to offshore obstacles and gradient. The Mulberry artificial harbours under construction wouldn't be operational until D+14. Rhino ferries were the only option for the critical first week when German counterattacks were most likely and Allied supply most tenuous. May brought final training exercises off the English coast. 60 ferry crews practiced loading, navigation, and beaching. The English Channel's conditions, cold water, strong tides, and unpredictable weather, revealed problems not apparent in Virginia. Tidal currents pushed ferries sideways, requiring constant helm corrections. Cold affected engine starting, particularly the grey marine diesels, which needed glow plugs heated before ignition. Fog reduced visibility to yards, making navigation by compass essential. The crossing distance posed new concerns. 3 miles in straight lines became 5 miles, accounting for currents and obstacles. At 5 knots, this meant 60-minute one-way trips, plus 20 minutes loading, plus 20 minutes unloading, plus return trip. Each ferry could complete 1 round trip every 2.5 hours in ideal conditions. 40 trucks per trip, 24 ferries operating, meant 384 trucks every 2.5 hours. The mathematics worked if nothing went wrong. June 1st brought final briefings. Vaghi assembled his ferry commanders, 37 officers who would lead the operations at Omaha and Utah beaches. The intelligence officer displayed reconnaissance photographs of the beaches. The Omaha Beach gradient was steeper than expected. Ferries would ground in 6 feet of water, requiring 100-foot ramps instead of 50-foot ramps. This meant cutting additional pontoon sections from the ferry platforms, reducing cargo capacity from 40 trucks to 36 trucks. The change cascaded through calculations, requiring more ferry trips to move the same tonnage. German beach defences visible in photographs included concrete obstacles, steel hedgehogs, and wooden stakes, all designed to rip bottoms from landing craft. Rhino ferries' flat pontoon bottoms might survive obstacle contact better than conventional hulls, or might be more vulnerable. Nobody knew. The ferries would find out by trial. The weather forecast for June 5th, the planned invasion date, predicted rough seas. General Eisenhower postponed the invasion 24 hours. June 6th forecast showed marginal improvement, barely acceptable. The decision to proceed meant ferries would operate in conditions exceeding their tested capabilities. Vaghi accepted this without comment. Everything about the invasion exceeded tested capabilities. Midnight, June 5th to 6th, 1944. The invasion fleet departed English ports. 156,000 soldiers travelled in 5,000 ships toward Normandy. Buried in cargo manifests and deck plans were pontoon sections for 60 Rhino ferries. The pontoons, each stamped with identification numbers, would either transform D-Day logistics or sink uselessly in the Channel. Lieutenant Commander Vaghi, aboard USS Samuel Chase, watched darkness hide the fleet and wondered which outcome awaited. Dawn, June 6, 1944. The Channel crossing revealed what no training exercise had prepared ferry crews for. Seas ran 6 feet, wind gusted to 20 knots, and rain reduced visibility to half a mile. Liberty ships anchored 3.5 miles offshore, further than planned due to underwater obstacles. The invasion beaches erupted with gunfire as assault waves struggled ashore, and scattered across dozens of ships, disassembled in pieces, the Rhino Ferries waited for assembly that couldn't begin until beaches were secure. Lieutenant Commander Vaghi reached Omaha Beach aboard an LCVP at 0800 hours. The scene defied description. Bodies floated in surf. Burning vehicles littered the sand. German artillery continued firing from bluffs overlooking the beach. The tide was rising, covering obstacles that had ripped apart landing craft during the first assault waves. Vaghi's mission, assembling Rhino Ferries in this chaos, seemed absurd. Yet cargo ships offshore held supplies that soldiers desperately needed. Without ferries, those supplies stayed aboard ships. The assembly plan required calm water near shore where pontoon sections could be bolted together. Reconnaissance had identified an area east of the main landing zone, partially sheltered by a rocky outcrop. Vaghi waded through waist-deep water toward this location. German machine gun fire cracked overhead. Mortar rounds burst in the surf zone. The protected assembly area was under direct observation from German positions on the bluffs. Assembly here was impossible. By noon on D-Day, the beach situation had stabilized enough for Vaghi to assess alternatives. The original assembly site was unusable. The beach itself offered no shelter. But 3 miles offshore, in the lee of the anchored Liberty ships, water was relatively calm. Ships themselves provided windbreaks. Their bulk offered concealment from shore observation. Vaghi made the decision that would define Rhino ferry operations. Assembly would occur offshore, at the transport anchorage itself, using pontoons lifted directly from ship holds and deck cargo. This created immediate problems. Pontoon sections weighed 1,200 pounds each. Ships' booms could lift them, but positioning 300 pontoons in correct sequence while floating required precision that seemed impossible in 6-foot seas. The alternative was assembling partial platforms that could be towed together and connected while afloat. Vaghi divided available pontoons into 10-section modules, each weighing 12,000 pounds, manageable by ship's cranes. The first module splashed into the water at 1400 hours on June 6 from SS James B. Weaver. Navy Seabees in an LCVP secured lines to the floating pontoon section, holding it against the ship's hull while a second module was lowered. Chief Petty Officer Robert Anderson, a pre-war ironworker from Pittsburgh, balanced on the first module with a socket wrench, aligning bolt holes as the second module swung down. Waves lifted both sections unpredictably. Anderson's hands, numb from cold water, struggled with nuts that had to be tightened to exact torque. Too loose and connections would fail under load. Too tight and bolts would strip. The first 2 modules connected after 40 minutes, twice the time required in calm water training. The combined 20-section platform measured 100 feet long and 10 feet wide, sufficient stability to support additional assembly work. Anderson's crew bolted on a third module, then a fourth. By 1800 hours, they had completed a 150 pontoon section, half a ferry. Darkness ended work for the day. June 7th began with urgent messages from shore. Cargo was piling up on beaches faster than available landing craft could move it from ships. LSTs had beached during high tide and were waiting 12 hours for the next tide to retract. Smaller landing craft were shuttling individual vehicles, but volume was far below requirements. Units ashore were rationing ammunition. Medical supplies were critically low. Vaghi ordered round-the-clock assembly operations. Work lights rigged on Liberty ships illuminated the anchorage after dark. Welding torches flared as crews reinforced pontoon connections. The scene resembled a floating industrial complex more than a military operation. Seabees worked in shifts, 4 hours on, 4 hours rest. Pontoon modules grew into platforms. Platforms grew into ferries. The first complete Rhino ferry, designated RF-1, was finished at 0300 hours on June 8, 36 hours after D-Day. RF-1 measured 210 feet long, 50 feet wide, and displaced 360,000 pounds. 4 grey marine diesel engines occupied pontoon sections at each corner. A wooden pilot house, constructed from salvaged lumber, provided weather protection for the coxswain. Ammunition boxes served as ballast to trim the platform level. The entire structure had been assembled while floating in open ocean under intermittent German artillery fire. It looked impossible and functional simultaneously. Ensign David Morrison, 23 years old, received command of RF-1. His previous seagoing experience totaled 8 weeks. He had never commanded any vessel before yesterday. Now he stood in a plywood pilot house controlling 4 diesel engines that together pushed 50,000 pounds of steel pontoons through Atlantic swells. Morrison engaged all 4 engines, felt vibration through the deck, and advanced throttles to half speed. RF-1 surged forward at 4 knots toward SS John W. Brown, a Liberty ship signalling cargo ready for transfer. The loading procedure had been practiced in calm Virginia waters. Reality off Normandy demanded improvisation. Liberty ships couldn't stop rising and falling with waves. The Rhino ferry alongside a ship would rise and fall differently due to different displacement. Bringing the ferry's deck level with the ship's cargo rail required matching their motion cycles, an impossibility. Morrison positioned RF-1 parallel to John W. Brown, maintaining 5 feet clearance, deck crews threw lines across. The ferry pulled against the ship's hull, fenders made from scrap rubber preventing metal-to-metal contact. Army trucks drove from the Liberty ship onto the Rhino ferry across a gangway consisting of 2 steel beams. The gangway angle changed constantly as both vessels moved with swells. The first truck inched forward, driver invisible inside the canvas-covered cab, wheels seeking purchase on steel slick with spray. The truck cleared the gap. Its 5-ton weight pressed the ferry lower in water. The second truck followed, then the third. Loading 40 trucks required 90 minutes, 3 times longer than planned. Morrison watched water levels rising on the ferry's deck edges as each vehicle added weight. At 36 trucks, the maximum capacity with extended ramps, the deck sat 8 inches above water. Waves washed across the pontoons, soldiers riding in truck beds huddled against spray. The ferry resembled a heavily loaded barge more than a vessel, barely floating, no freeboard, moving through determination rather than design. Morrison engaged engines and turned toward shore. The loaded ferry responded sluggishly. Speed dropped to 3.5 knots. The 3-mile journey would require 50 minutes. German artillery batteries on the bluffs behind Omaha Beach had excellent observation of the anchorage. Every ferry moving shoreward presented an unmissable target, 210 feet long, 50 feet wide, carrying visible cargo that exploded if hit. The first German shell landed 200 yards ahead at 09:15 hours. Morrison had no evasive options. The ferry couldn't accelerate, couldn't turn quickly, couldn't stop. It could only continue plodding toward the beach at 3 knots. The second shell splashed 100 yards to port. German gunners were bracketing the range. The third shell would likely hit. Morrison ordered all personnel to lie flat on deck. 36 truck drivers, 8 ferry crew, and 47 soldiers riding in truck beds pressed themselves against steel and wood. The third shell struck the water 15 yards to starboard. Shrapnel peppered the ferry's side pontoons. Morrison heard hissing as compressed air escaped from a penetrated section. 1 pontoon damaged from 300 total. The ferry's motion changed slightly, listing 1 degree to starboard, but buoyancy remained adequate. The 4th shell never came. Allied destroyers offshore had located the German battery through its muzzle flashes and were firing counter-battery missions. Morrison continued toward the beach, ferry listing slightly, 1 pontoon taking water, but cargo intact and crew alive. The crossing that should have taken 50 minutes required 75 due to the damaged pontoon's increased drag. Beaching procedure required driving the ferry's bow directly onto sand until forward momentum stopped. The hinged ramp sections, each 50 feet long, would then be lowered from the bow, extending across the surf zone to dry beach. Trucks would drive off in single file. The process assumed sufficient approach speed to drive the ferry firmly aground. Morrison's damaged ferry, moving at 2 knots instead of 4, lacked that momentum. RF-1's bow touched sand at 10 knots forward speed. The platform's weight, 400,000 pounds with cargo, should have driven it firmly aground. Instead, a wave lifted the stern just as the bow grounded. The ferry pivoted on its bow, swinging sideways. Morrison reversed engines to halt the swing, but grey marine diesels lacked reverse power. The ferry broached parallel to the beach, side on to waves. Seabees in the water worked to maneuver ramp sections into position. The surf zone at Omaha Beach ran 150 feet wide at this tide stage. Standard 50-foot ramp sections couldn't span that distance. Crews connected 3 ramp sections end to end, creating a 150-foot causeway from ferry to beach. The improvised structure flexed alarmingly as waves passed under it, but held together. Trucks drove off one at a time, spacing themselves along the ramp to distribute weight. Each truck's movement shifted the ferry's trim, causing it to settle deeper or rise slightly depending on remaining cargo distribution. The 36th truck cleared the ferry at 1100 hours. RF-1 sat empty, listing further to starboard as the damaged pontoon continued flooding. Morrison ordered engines ahead, attempting to back away from the beach. The ferry pivoted its stern away from shore, but the bow remained grounded. Seabees attached tow lines to the ferry's stern. An LCM, landing craft mechanized, added its engine power to RF-1's engines. Combined thrust pulled the ferry backward off the beach into deeper water. The damaged pontoon was now 1/3 full of seawater, adding 6,000 pounds of weight that reduced speed to 2 knots for the return trip to the transport anchorage. Morrison's first ferry run had delivered 36 trucks, but demonstrated that everything about Rhino ferry operations was harder than training had suggested. By June 8th evening, 6 Rhino ferries were operational. Vaghi organised them into shifts, 3 ferries loading at transport ships, 3 ferries unloading at beaches. The cycle time, 2.5 hours per round trip in training, was running 4 hours in combat conditions. This meant each ferry completed 6 trips per day instead of 9. 6 ferries making 6 trips, carrying 36 trucks, each meant 1,296 trucks daily. This exceeded all landing craft combined, but fell short of the planned 2,000 vehicles daily that 60 ferries would deliver. Assembly continued around the clock. By June 9th, 12 ferries were operating. June 10th brought 18 ferries. The assembly rate had improved as crews gained experience working in offshore conditions. Pontoon modules were now connected in 50-section increments rather than 10-section modules. This reduced connections required and accelerated construction. A complete ferry could be assembled in 24 hours instead of 48. The pontoon supply presented unexpected challenges. Each ferry consumed 300 pontoons. 60 ferries required 18,000 pontoons. These had been distributed across 148 Liberty ships, but those ships had arrived on different schedules. Some anchored far from the assembly areas. Others needed their pontoon cargo offloaded to access more critical supplies underneath. Coordinating pontoon availability required constant communication between ships, shore parties, and assembly crews. Vaghi established a pontoon depot at the transport anchorage, a designated water area where ships could discharge pontoons that weren't immediately needed for ferry construction. Pontoons were towed together in rafts of 50 sections, marked with flags, and held in position by small boats. The depot functioned as a floating warehouse, storing pontoons until assembly crews needed them. At peak operations, the depot held 700 pontoons, enough for 2 complete ferries. Weather remained the greatest operational constraint. Channel seas ran 6 feet or higher on 12 of the first 20 days after D-Day. Ferries could operate in these conditions, but loading times doubled. Cargo shifted in rough seas despite chains securing trucks to deck. One ferry, RF-7, lost 3 trucks overboard when chains parted during a particularly violent wave. The trucks, fully loaded with ammunition, sank in 60 feet of water. The loss represented 6 tons of critical cargo and demonstrated the margins within which ferry operations functioned. German air attacks intensified on June 13th. Luftwaffe bombers, operating at night, targeted the transport anchorage where ships and ferries concentrated. RF-11 took a near miss from a 500-pound bomb that detonated 20 feet from the ferry's stern. The explosion lifted the entire aft section out of water, cracked welds on 6 pontoon connections, and disabled 2 engines. The ferry remained afloat, its distributed buoyancy preventing catastrophic failure, but required towing to shore for repairs. Damage assessment determined that 8 pontoon sections needed replacement. The ferry was reconstructed using pontoons from the depot and returned to service after 36 hours. The resilience surprised everyone. A conventional ship's hull, penetrated or cracked, would flood and sink. Rhino Ferries' modular construction meant damage remained localized. 1 destroyed pontoon affected only that section. The remaining 299 pontoons continued providing buoyancy. Ferries could sustain multiple hits and continue operating. This, accidental survivability, became intentional doctrine. Ferries absorbed damage that would have sunk landing craft, completed their missions, and were repaired using replacement pontoons. By June 20th, D+14, 48 Rhino ferries operated at the Normandy beaches. They had delivered 18,400 vehicles, 62,000 tons of cargo, and 93,000 personnel. These numbers exceeded combined totals for all LSTs operating in the same period. The ferries had vindicated their design, not through elegance or efficiency, but through sheer capacity. They moved more cargo because they carried more cargo. The mathematics was simple. The execution had been anything but simple. The Mulberry artificial harbours became operational on June 20th, providing protected berthing for Liberty ships to discharge directly to piers. This should have reduced ferry requirements. Instead, ferry operations intensified. The harbours could accommodate 24 ships simultaneously. Over 100 ships waited in the anchorage. Ferries provided discharge capacity for ships that couldn't enter the Mulberries. The ferry operations that were supposed to be temporary became permanent features of Normandy logistics. Maintenance emerged as the critical challenge. Grey marine diesel engines, designed for submarine chasers, weren't meant for continuous operation. They overheated, developed oil leaks, and suffered electrical failures. Each ferry carried 4 engines, providing redundancy, but when 2 engines failed, the ferry couldn't maintain speed. RF-23 operated for 16 hours on a single functioning engine, moving at 1 knot, but completing its mission. Spare engines weren't available. Maintenance crews cannibalized parts from disabled ferries to keep others operational. The pontoons themselves deteriorated under continuous use. Salt water corroded bolt connections. Welds cracked from constant flexing. Wooden decking, installed to protect pontoon tops from vehicle weight, splintered and required replacement. Each ferry needed daily inspection and weekly major maintenance. Vaghi established a rotation system where 1/6 of the ferry fleet was in maintenance status at any time. This reduced operational ferries but prevented catastrophic failures from deferred maintenance. Personnel exhaustion exceeded equipment fatigue. Ferry crews worked 18-hour days. Assembly crews worked 20-hour days. The 8-man ferry crew handled all aspects of operation: navigation, engineering, cargo loading, beaching, unloading, and damage control. There were no specialists. Everyone did everything. Ensign Morrison, after 3 weeks commanding RF-1, had lost 20 pounds and developed a hand tremor from engine vibration. He continued operating because no replacement existed. The British beaches, Gold, Juno and Sword, initially planned to receive 30 Rhino ferries, received only 12. The remaining 18 ferries were redirected to Omaha and Utah beaches where American logistics concentrated. This decision reflected different operational philosophies. British forces emphasized port capture and used ports for supply. American forces built logistics infrastructure at beaches and sustained operations without ports. Rhino ferries enabled the American approach. Cherbourg fell to American forces on June 26. The port, anticipated to provide major cargo capacity, was so thoroughly destroyed by German demolitions that engineers estimated 3 months before significant operations could begin. Ferries continued carrying the supply burden. By end of June, ferry operations at Normandy had moved 42,000 vehicles and 135,000 tons of cargo. No alternative existed. Without ferries, the Allied advance would have stalled at Normandy beaches. The storm that struck Normandy from June 19th to 22nd tested every aspect of ferry operations. Wind reached 60 miles per hour. Seas ran 12 feet. The Mulberry Harbour at Omaha Beach was destroyed. Ships dragged anchors. Landing craft sank at their moorings. Rhino Ferries, considered the most vulnerable vessels in the fleet, survived with damage, but not destruction. Vaghi ordered all ferries beached during the storm. They were deliberately grounded at high tide, allowing the falling tide to leave them resting on sand. The storm surge lifted them and threw them higher on the beach. Some ferries were deposited 100 yards inland. All survived. When the storm passed, tractors dragged the ferries back to water. Pontoon sections were damaged, engines filled with sand, and control systems destroyed, but the basic structures remained intact. Within 72 hours, 38 of the 48 ferries returned to service. The storm validated the fundamental design insight. Flexibility, considered weakness in conventional naval architecture, proved to be strength. The ferries survived not despite their improvised construction but because of it. Bolted sections flexed without breaking. Independent pontoons absorbed impacts without transmitting damage. The absence of rigid hull structure meant nothing could crack catastrophically. The ferry's inability to sink, even when heavily damaged, resulted from having 300 separate buoyancy chambers instead of one hull compartment. July brought different challenges. Allied armies advancing inland needed fuel more than vehicles. Ferries adapted to carry fuel trucks exclusively. A ferry carrying 45,000-gallon tanker trucks delivered 200,000 gallons per trip. 6 ferry trips daily meant 1.2 million gallons daily from a single ferry. 12 ferries dedicated to fuel transport delivered 14 million gallons daily, sufficient for 4 armoured divisions. The ferries had become rolling pipelines, delivering fuel faster than any other system. The transformation extended beyond fuel. Ferries carried artillery ammunition, with 40 trucks each loaded with 10 tons of shells, 400 tons of ammunition per trip. They carried medical supplies, with ambulance trucks transporting wounded from beach hospitals to hospital ships. They carried engineering equipment, bringing dozers, graders, and construction materials for airfield construction. Whatever needed movement from ships to shore went by ferry. By August, 72 Rhino ferries operated at Normandy, exceeding the original 60-ferry plan. Additional ferries had been constructed from pontoon reserves and salvaged materials. Some incorporated pontoon sections recovered from storm-damaged Mulberry harbours. Others used pontoons originally intended for bridge construction. The ferries had evolved from emergency stopgap to permanent infrastructure. Lieutenant Commander Vaghi submitted his after-action report in September 1944. The statistics were comprehensive. 72 ferries had completed 14,200 trips. They had delivered 63,000 vehicles, 490,000 personnel, and 280,000 tons of cargo. 23 ferries had been damaged by enemy action. 14 ferries had been destroyed by weather. All but 4 were repaired and returned to service. No ferry had been sunk by enemy action. Combined ferry operations had exceeded all landing craft types combined for sustained cargo delivery. The report's conclusion recommended Rhino ferry adoption as standard amphibious equipment for future operations. Vaghi noted that ferries required no shipyard construction, could be assembled from standard components, adapted to any beach condition, and survived damage that sank conventional vessels. The unspoken subtext was clear. The improvised platform assembled from bridge pontoons and outboard motors had revolutionized amphibious warfare. The Rhino ferry concept would soon face its ultimate test across the Pacific, where distances exceeded anything in Europe, where Japanese defenses had been refined through years of preparation, and where every principle proven at Normandy would be challenged by conditions that made the English Channel seem benign. The engineers who had designed floating platforms never intended for ocean crossings were about to discover that their creation could function in ways they never imagined. But that story, and the mathematical impossibilities it would overcome, awaited in theatres where the stakes would be even higher than France. November 12, 1944, Leyte Gulf, Philippines. Commander Harold Benson watched 28 Rhino ferries work the beaches in conditions that would have been considered impossible 6 months earlier. Typhoon swells ran 8 feet, Japanese artillery fired from hills 3 miles inland. Coral reefs extended 500 yards offshore, preventing LST beachings. The ferries shuttled between Liberty ships anchored in deep water and beaches that conventional doctrine said couldn't be supplied. They were delivering 4,000 tons of cargo daily. The Pacific demanded everything Normandy had taught and more. Distances between islands measured hundreds of miles, not 3 miles from ship to shore. Coral reefs surrounded most invasion beaches, creating obstacles far more dangerous than German steel hedgehogs. Typhoons struck with greater frequency and violence than channel storms. Japanese defenders fought with intensity that exceeded anything in Europe, and the cargo requirements, sustaining campaigns across an ocean, dwarfed European operations. Rhino ferries arrived in the Pacific Theatre in August 1944. The first deployment was Peleliu, where reef systems prevented LST operations entirely. Engineers assembled 12 ferries from pontoons carried aboard ammunition ships. The ferries operated in coral-studded waters that would have ripped conventional hulls apart. Pontoon bottoms scraped over coral with grinding sounds that terrified crews, but the distributed buoyancy meant even multiple punctures couldn't sink the platforms. Ferries with 6 damaged pontoons continued operating at reduced capacity. Leyte brought scale. The invasion required landing 133,000 personnel and 200,000 tons of supplies in the first month. Planner calculated requirements and concluded they needed 120 Rhino ferries. Pontoon production had ramped up specifically for Pacific operations. Manufacturers were delivering 50,000 pontoons monthly. Assembly crews, trained at Normandy, transferred to Pacific fleets, bringing hard-won expertise. The assembly process in the Pacific refined techniques developed in France. Ferries were now built in 4 separate 75 pontoon sections that could be towed independently and connected at the invasion site. This distributed assembly across multiple ships and reduced vulnerability to single-point failures. If one ship was sunk carrying pontoons, 3/4 of a ferry's components remained available on other vessels. The modular approach also allowed ferries to be sized for specific missions. A ferry for artillery pieces needed only 200 pontoons. A ferry for fuel trucks needed all 300. Okinawa, in April 1945, pushed ferry operations to theoretical limits. The invasion force included 182,000 personnel requiring sustained supply over beaches lacking any port facilities. 64 Rhino ferries worked continuously for 3 months. They delivered 894,000 tons of cargo, more tonnage than all Atlantic ferry operations combined. The ferries operated through 2 typhoons, constant Japanese kamikaze attacks, and artillery fire from defenders who held positions overlooking the beaches for months. The kamikaze threat created new tactical requirements. Ferries loaded with fuel trucks or ammunition couldn't risk attacks by suicide aircraft. Operations shifted to night loading and dawn crossings when Japanese air attacks were less frequent. Ferries painted flat black became nearly invisible against dark water. They moved without running lights, navigating by compass and shore recognition. The slow speed that made ferries vulnerable to artillery made them difficult targets for aircraft seeking fast-moving vessels. Ferry losses in the Pacific totaled 18 vessels destroyed and 42 damaged but repairable. Remarkably, no ferry was sunk by enemy action. Typhoons destroyed 11 ferries by throwing them onto reefs or coral shelves where recovery was impossible. 7 ferries were scuttled after sustaining damage that required more repair time than operational schedules allowed. But in every case, pontoons were salvaged and reused. The modular construction that made ferries easy to build made them equally easy to cannibalize. The versatility expanded beyond original design parameters. Ferries towed damaged landing craft to repair facilities. They served as floating storage for ammunition too dangerous to keep ashore. They functioned as helicopter landing platforms before dedicated helicopter carriers existed. One ferry at Iwo Jima was converted to a floating hospital, with medical tents erected on its deck, treating wounded who couldn't be evacuated immediately. The pontoon platform that began as a cargo carrier became whatever the situation required. By war's end in August 1945, 273 Rhino ferries had been constructed across both theatres. They had delivered over 2 million tons of cargo, transported 700,000 vehicles, and moved 3.8 million personnel. The ferries had operated on 4 continents, functioned in conditions from Arctic Norway to tropical Pacific atolls, and survived everything from German 88mm artillery to Japanese 1,000-pound bombs. The cost per ton delivered told the economic story. Rhino ferries cost $42,000 to construct. An LST cost $1 million. A ferry could deliver 36 vehicles per trip in 4 hours, including loading and unloading. An LST delivered 30 vehicles per trip in 12 hours, including beaching and retracting. Over a 30-day operational period, one ferry delivered 10,800 vehicles. One LST delivered 1,800 vehicles. The ferry cost 4% of the LST and delivered 6 times the cargo volume. Production statistics revealed industrial impact. Ferry operations consumed 91,000 pontoons, requiring production capacity from 47 manufacturers across 19 states. Grey Marine diesel engines, originally cancelled after submarine chaser program ended, found new purpose powering ferries. Over 1,000 engines were remanufactured from storage specifically for ferry use. The ferries created demand for products that would otherwise have been military surplus, converting potential waste into operational assets. The personnel requirements were equally significant. Ferry operations employed 16,000 sailors and soldiers as crew members, assembly personnel, and maintenance staff. These were individuals who required minimal specialized training. Ferry coxswains needed 2 weeks of instruction. Assembly crews needed 1 week. Maintenance personnel needed basic mechanical aptitude. The ferries democratized naval operations, allowing men with no maritime background to conduct amphibious logistics. This contrasted sharply with LST operations requiring trained naval personnel with months of instruction. Post-war analysis by the Navy's Bureau of Ships concluded that Rhino ferries had been essential to Allied victory in both theatres. The report, declassified in 1967, stated that without ferries, Operation Overlord would have required an additional 6 months of landing craft construction before sufficient capacity existed. Pacific operations would have been delayed indefinitely. The improvised platform, built from bridge pontoons, had altered the timeline of World War II itself. The technical achievement was capturing professional attention. Naval architects who had dismissed the ferry design as impossible now studied why it worked. The answers contradicted conventional wisdom. Flexibility under load, considered structural weakness, distributed stresses that would have fractured rigid hulls, flat bottom design, rejected as hydrodynamically inefficient, provided stability in surf zones where conventional bows would have buried. Modular construction, thought to compromise strength, created redundancy that prevented catastrophic failure. Every supposed flaw was actually advantage in the specific operational environment. The Rhino ferry influenced post-war amphibious doctrine fundamentally. The concept of assembling logistics infrastructure from modular components rather than constructing purpose-built vessels became standard practice. Causeway sections used in every amphibious operation since 1945 descended directly from ferry pontoons. The Army's logistics over-the-shore systems employed in Korea, Vietnam, and Persian Gulf operations used principles developed during ferry operations. The ferries proved that improvisation could outperform planning when improvisation addressed actual requirements rather than theoretical specifications. Several ferries survived the war and found civilian applications. 4 ferries were sold to Alaska construction companies and operated as vehicle ferries in Prince William Sound until the 1970s. 2 ferries were converted to floating logging platforms in the Pacific Northwest. 1 ferry became a commercial barge on the Mississippi River, carrying grain until 1981. The last known operational Rhino ferry sections, identified by original Army pontoon serial numbers, were discovered in 2003 at a boatyard in Louisiana, still functioning as floating dock sections 58 years after their manufacture. The engineers who created the Rhino ferry received limited recognition. Captain John Hughes, who authorized the initial experiments, retired from the Navy in 1946 with the Legion of Merit. Lieutenant Albert Doyle, the civil engineer who designed the first prototype, returned to civilian practice and never worked on naval projects again. Chief Warrant Officer William Sullivan, who solved the propulsion challenges, was killed in a training accident in 1945 before seeing the Pacific ferry operations his innovations enabled. The thousands of assembly crews, maintenance personnel, and ferry operators who made the system function received campaign medals identical to those earned by every serviceman. No special recognition existed for revolutionizing amphibious warfare. Lieutenant Commander Joseph Vaghi, who commanded ferry operations at Omaha Beach, submitted his final report in October 1945 with observations that captured the ferry's essence. He wrote that the Rhino ferry succeeded because it solved the actual problem rather than the anticipated problem. Planners expected to need faster vessels. They actually needed larger vessels. Planners expected to need maneuverable craft. They actually needed stable platforms. Planners expected to need sophisticated ships. They actually needed simple barges. The ferries worked because someone asked what was truly necessary rather than what was conventionally correct. The morning of June 7, 1944, when Lieutenant Commander Vaghi stood on a floating steel platform that shouldn't exist, he witnessed the validation of necessity over convention. The Rhino ferry carried 40 trucks because 40 trucks needed carrying. It crossed 3 miles of ocean because 3 miles separated ships from shore. It survived German artillery because cargo had to reach beaches regardless of fire. Every aspect of its design emerged from requirements, not theory. 273 ferries, assembled from 91,000 pontoons, powered by 1,000 repurposed engines, crewed by 16,000 men with minimal training, delivered 2 million tons of cargo that sustained Allied armies from Normandy to Okinawa. They proved that engineering excellence sometimes means building what works rather than what's elegant. That innovation often emerges from desperation rather than inspiration, and that the most effective solution to an impossible problem might be a platform welded together from bridge parts that naval architects never imagined could float, much less fight a war. The Rhino ferries didn't just move cargo. They demonstrated that in warfare, as in engineering, the audacious improvisation that addresses reality will always outperform the perfect design that addresses theory. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.